Alright, this is the second video, January the 10th, for RMA 18-120 for electronic and engineering designs. And what we're going to show here is that the board is going to be working okay for a full wave rectifier, as long as we verify that we have the right connections and we have the right load. What we have here is the same wiring board, serial number 33266. And the first thing that we're going to do is we're going to power with 120 across positions 3 and 5. There's 3 and 5, the last two on the left, the one in the middle and the one on the right. That's the 120. Again, as we pointed out, we have the two red LEDs on and the green LED. Can you see it, Miguel? The green LED on, pointing out that we have power. Now, we're not going to be able to do anything until we clear that phase loss LED. And what we've done for this application per the customer requirements is we have 240 3-phase source that it's going to Variac. We have already selected 12 volts AC going in, and what we're doing is we're also taking, there's a 12 volts, and here we are splitting the 12 volts, and we are using 3 half a watt 68.1K resistors. For the 12 gets attenuated by 68.1, and that gets fed into, on this particular board, on J7A, although we anticipate that it'll probably be better if the customer uses J7B, which happens to be whether it's 7JA or J7B, it has to be the 12 volts going through 368.1 inline resistors to attenuate that. So now that we apply the 240, we selected 13.3. That's what we have face to face. With the 3 resistors attenuating that signal, we have cleared the phase loss LED. So now the only LED that remains on, it's the inhibit, and that's because, or switch, it's telling it to be enabled. And sig high, it's a 0 to 5. Can you bring in that scope, Tony, so that we measure sig high? Alright, so that's our output. Here we have our 6 SCRs and a rectifier. The load, the output of that comes to this light bulb, which is our load. We're looking across that with an oscilloscope, and we are also looking at the DC output with a multimeter. So we have the AC input and the output. The output is at 0 right now because the board is inhibited. Sig high, it's low at 0. You can see that I can vary, but no matter what I do, the board is inhibited. And we notice though, however, we have the same 2 test points on position, on test point 5, the reference, and test point 3 is the delay angle. So we're measuring this delay, which is 140 from this H right here to here, and that's 148. And as sig high increases, that will be reducing. That will get reduced, so that we have 148 degrees right now, and the output is 0. So let's go ahead and enable. So we have enabled the board. Now there's no LED on it. The output is low. Sig high is 0, but now we see an output. Go ahead and inhibit, Tony, so that we see there's nothing there. So go ahead and bring it in, and go ahead and start slowly increasing. So we see that you're at 1 volt. We see the delay angle closing in. Now the SCRs are firing. You can stop right there, Tony. At 3.86, the board is set up for 0 to 5. At 3.8, this is the output from the SCRs. That's what the SCRs are firing. The delay angle now, it's 42.5 degrees. Again, we've noticed that this area right here has been reduced, and there's hardly any light on that bulb. However, we're showing 9 volts, and the output is 12 volts. Go ahead and put it all the way to 5, Tony, please. Now at 5.02, which is the maximum, we have the maximum output. We have the minimum delay angle, 13.6 degrees. We see a brighter light on the light bulb, and we have 12.5 and 11.5, 12.5 DC and 11.4 volts AC. And if I were to increase this, the variac, whether it's 11 or 12 or 13 or 14 or 15, the delay angle will remain the same. It's just that the output will increase as long as we keep 6 high constant. The most important thing is that the 68.1K resistors attenuating the phasing will be plenty to provide the correct phase referencing. This is the end of this video.